Bayesian estimation of the parameters of a function. We now discuss the case where we estimate the parameters, not of a distribution, but some function of the input, for regression or a classification. Again, our approach is to consider these parameters as random variables with a prior distribution and use Bayes' rules to calculate a posterior distribution. We can then either evaluate the full integral, approximate it, or use the MAP estimate. Regression. Let us take the case of a linear regression model. R equals to W transpose times X plus epsilon, where epsilon is the noise or error of which is approximated by the normal distribution with mean 0 and also beta to the -1, where beta is the precision of the additive noise. The parameters are the weights W, and we have a sample X, which is equals to the set X to the T, Y to the T, and the T starting from 1 to N, where X is defined in R to the D, and R to the T is in R, which we can break down into a matrix of inputs and a vector of decided outputs as X equals to the set XR from equation 14.10. We have P of R to the T conditioning on X to the T W beta, which is approximately by n of W to the T times X and the beta to the inverse. We saw previously in section 4.4 that the log likelihood is L of X conditioning on W, which is by definition of log of P of X conditioning on W, which is log of P of R X conditioning on W, which is equals to log of P of R conditioning on XW. Now we remove the X to the back side of the condition, plus log of P of X, where the second term is a constant, independent of the parameters. We expand the first term as L of R conditioning on X W beta, which is equals to log of pi of P of R to the T conditioning on X to the T W beta, where pi is taken among all possible T, which is minus n times log of the square root of 2 pi plus n times log of beta minus beta divided by 2 times sigma of R to the T minus W to the transpose times X to the T then to the square, summing for index T. For the case of the ML estimate, we find W that maximizes this, or equivalently minimizes the last term, that is the sum of the squared error, which can be rewritten as E equals to R minus XW to the transpose times R minus XW. Taking the derivative with respect to 2W and setting it to 0, we get the maximum likelihood estimator. We have previously derived this in section 5.8. That is WML equals to X transpose times X, such a value to the inverse, then times X transpose, then times R. Having calculated the parameters, we can now do prediction. Given new input X to X prime, the response is calculated as R prime equals to W ML to the transpose times X prime. For nonlinear models, G of X conditioning on W, for example, a multi-layer perceptron where W are all the weights. We minimize, for example, using gradient descent. The expectations of X conditioning on W equals to the square of the value R to the T minus G of X to the T conditioning on W. In the WLSQ that we minimize, it is called the least squares estimator. Then the prediction is calculated as R prime equals to G of X prime conditioning on W LSQ. In the case of the Bayesian approach for the parameters, we define a Gaussian prior P of W, which is approximated by n of 0 alpha to the inverse times the identity matrix I, and which is a conjugate prior, and for the posterior, we get P of W conditional X, which is approximately by the normal distribution, the Gaussian distributions of mu n and sigma n, where mu n is beta times sigma n times X to the transpose times R, and sigma n is equals to the inverse of alpha times identity I plus beta times x transpose then times x, such an inverse. To calculate the overall output, we integrate over the full posterior. Alpha prime equals to the integrations of w transpose times x transpose times p of w conditioned on x dw, integrating for all of this. And if we want to use a point estimate, the MAP or Bayes, because the posterior is Gaussian, estimator is Wmap equals to mu n, which is equals to beta, times the inverse of alpha I plus beta times x transpose times x. Then, after the inverse times x transpose, then times alpha. And we replace the density with a single point, namely the mean alpha prime equals to Wmap to the transpose times x prime with variance. Variance of alpha prime equals to beta to the inverse plus x prime to the transpose times sigma, summing for all x prime, summing for all n, comparing equation 14.16 with the ML estimate of equation 14.12. This can be seen as regularization. That is, we add a constant alpha to the diagonal to better conditioning the matrix to be inverted. The prior P of W approximated by n of 0 alpha to the inverse times I says that we expect the parameters to be close to 0 with a spread inversely proportional to alpha. When alpha is approaching 0, we have a flat prior and the MAP estimate converges to the ML estimate. We see in figure 14.4 that if we increase alpha, we force parameters to be closer to 0 and the posterior distribution moves closer to the origin and shrinks. If we decrease beta, we assume noise with higher variance and the posterior also has higher variance. If we take the log of the posterior, we have log of P of W conditional x alpha, which is proportional to log of P of x alpha conditional W plus log of P of W, which is proportional to log of P of alpha conditional xw plus log of P of W, which is equal to minus beta over 2 times sigma of the square of alpha to the t minus W transpose times x to the t, where this sigma is for summing up for all t, minus alpha over 2, then times W transpose, then times W, then plus constant c, which we maximize to find the MAP estimate. In the general case, given our model G of x conditional on W, we can write an augmented error function. E reach of W conditional x equals to sigma, summing for all t of the term, the square of alpha to the t minus G of x to the t conditional on W, plus lambda times sigma of Wi to the square, summing for all I, with the lambda, which is, by definition, the ratio of alpha divided by beta. This is known as the parameter shrinkage or ridge regression in statistics. In section 4.8, we call this regularization, and in section 11.9, we call this weight decay in neural networks. The first term is the negative log of the likelihood, and the second term penalizes Wi away from 0 as dictated by alpha of the prior. Though this approach reduces sigma of Wi squared, summing for all I, it does not force individual Wi to 0, that is, it cannot be used for feature selection, namely to determine which xi are redundant. For this, one can use a Laplacian prior that uses the L1 norm instead of the L2 norm. That is, P of W conditioning alpha equals to pi multiplying for all I of the term alpha divided by 2, then to the exponential of minus alpha times the absolute values of Wi, which is equals to alpha divided by 2 to the d, then times exponential of minus alpha times sigma of the absolute value of Wi, summing for all I. Now, figure 14.4 is the comparison of different alpha and beta, and also the prior and the posterior. Bayesian linear regression for different values of alpha and beta. To the left, crosses are the data points, and the straight line is the ML solution. The MAP solution with one standard deviation error, bars are also shown dashed. Center is the prior density centered at 0 and a variance 1 over alpha. To the right, posterior density, whose mean is the Wmap solution. We see that when alpha is increased, the variance of the prior shrinks and the line moves closer to the flat 0 line. When beta is decreased, more noise is assumed and the posterior density has higher variance. The posterior probability is no longer Gaussian, and the Wmap estimate is found by minimizing E lasso of W conditional x, which is equal to sigma of the square of r to the t minus W transpose times x to the t, summing for all t plus the term 2 times sigma square times alpha times sigma of the absolute values of Wi, summing for I, where sigma square is the variance of noise for which we plug in our estimate. This is known as lasso, least absolute shrinkage, and a selection operation. Tipsirani in 1996. To see why L1 induces sparseness, let us consider the case with two weights, the transpose of W1, W2. That is, the true norm of 1, 0 to the transpose, which is equal to the true norm of the transpose of 1 divided by the square root of 2, 1 divided by the square root of 2. And such a norm in true norm is equal to 1, and where the 1 norm of the transpose of 1, 0 is equal to 1, which is less than the 1 norm of the transpose of 1 divided by the square root of 2, 1 divided by the square root of 2, which is equal to the square root of 2, and therefore L1 prefers to set W2 to 0 and use a large W1, rather than having small values for both. The use of basis kernel functions. Using the Bayer's estimate of equation 14.14, the prediction is written as alpha prime equals to x prime to the transpose times W, which is equal to beta times x prime to the transpose times sigma n of the term x to the transpose times r, which is equal to sigma summing for all t of the term beta of x prime to the transpose. If we put this term inside of sigma, and then of the sigma term, sigma n times x to the t times alpha to the t. This is the dual representation when we can write the parameter in terms of the training data, or a subset of it, as in support vector machines, chapter 13, we can write the prediction as a function of the current input and the paste data. We can rewrite this as alpha prime equals to sigma summing for all t of the term k of x prime x to the t, then such a k value times r to the t, where we define k of x prime x to the t equals to beta of x prime to the transpose times sigma n of the term x to the t. We know that we can generalize the linear kernel of equation 14.19 by using a nonlinear basis function phi of x to map to a new space where we fit the linear model. In such a case, instead of the d-dimensional x, we have the k-dimensional phi of x, where k is the number of basis functions, and instead of m by d data matrix x, we have m by k image of the basis function phi. And during test, we have alpha prime equals to phi of x prime to the transpose times w, where w is equal to beta times sigma n to the phi of the term phi to the transpose times alpha, and sigma n to the phi of it is equals to the inverse of alpha times I plus beta times phi to the transpose then times phi again. And if we simplify the previous formula, that will be beta times phi of x prime to the transpose times sigma n to the phi times phi to the transpose times alpha, which is equal to sigma t of beta times phi of x prime to the transpose times sigma n to the phi times phi of x to the transpose times alpha to the x to the t times alpha to the t, which is equals to, if we simplify all of them, sigma, summing for all t of k of x prime, x to the t, then times alpha to the t, where we define k of x prime, x to the t equals to beta times phi of x prime to the transpose times sigma n to the phi of the term phi of x to the t as the equivalent kernel. This is the dual representation in the space of phi of x. We see that we can write our estimate as a weighted sum of the effects of instances in the training set where the effect is given by the kernel function k of x prime x to the t. This is similar to non-parametric kernel smoothers we discussed in Chapter 8, or kernel machines of Chapter 13. Error bars can be defined using variance of alpha prime equals to beta inverse plus phi of x prime to the transpose times sigma n to the phi of the term phi of x prime. An example is given in figure 14.5 for the linear, quadratic, and the fourth degree kernels, just as in a regression proper, where we can work on the original x for phi of x. In Bayesian regression, too, we can work on the pre-processed phi of x, defining parameters in that space. Later on in this chapter, we are going to see Gaussian processes where we can define and use k of x to the t directly without needing to calculate phi of x. Bayesian classification. In a two-class problem, we have a single output, and assuming a linear model, we have p of c1 conditioning on x to the t, which is equals to y to the t, which is equals to the output of sigmoid of w transpose times x to the t. The log likelihood of a Bernoulli sample is given as L of alpha conditioning on x equals to sigma, summing for all t of r to the t times log of yt plus 1 minus alpha to the t times log of 1 minus y to the t, which we maximize or minimize is negative log the cross entropy to find the ML estimate, for example using gradient descent. This is called logistic discrimination. Section 10.7. In the case of the Bayesian approach, we assume a Gaussian prior, P of W equals to the normal distributions of M0, S0. And the log of the posterior is given as log of P of W conditioning on alpha x, which is proportional to log of P of W plus log of P of alpha conditioning on Wx, which is equals to minus 1/2 times W minus M0 to the transpose times S0 to the inverse times W minus M0 plus sigma of summing for all t of alpha to the t times log of yt plus 1 minus r to the t times log of 1 minus y to the t, then plus constant c. Now figure 14.5 is the Bayesian regression using kernels with one standard deviation error bars. A. Linear, that is phi of x equals to 1x to the transpose. B. Quadratic, that is phi of x equals to 1x squared to the transpose. And C. Fourth degree, that is phi of x equals to 1x squared x to the third x to the fourth to the transpose. Now, this posterior distribution is no longer Gaussian. That means that the log of P of W conditioning on alpha x, such a posterior distribution, is no longer Gaussian, and we cannot integrate exactly. We can use a Laplace approximation, which works as follows. This is proposed by McKay in 2003. Let us say we want to approximate some distribution f of x not necessarily normalized to integrate it to 1. In Laplace approximation, we find the mode of f of x, x0, fit a Gaussian q of x, centered there, and then if we want to integrate, we integrate this fitted Gaussian instead. To find the variance of the Gaussian, we consider the Taylor expansion of f dot at x equals to x0, that is log of f of x equals to log of f of x0 minus 1/2 times a times x minus x0 to the square, and so on, where a is defined by minus d divided by d x squared of the term log of f of x, where the x is substituted with value x0, and note that the first linear term disappears because the first derivative is 0 at the mode. Taking exponential, we have f of x equals to f of x0 times exponential of minus a divided by 2, then times x minus x0 to the square. To normalize f of x, we consider that in a Gaussian distribution, the integrations of 1 divided by the square root of 2 pi times 1 over the square root of alpha. This is in a denominator. Then times exponentials of minus a over 2 times x minus x0 to the square. Such integration is equals to 1. And that means that the integration of just the term, if we remove those constants out of the previous integration, then the integrations of the exponential of minus a over 2 times x minus x0 to the square is equals to the square of a divided by 2 pi, and therefore q of x is equals to the square root of a divided by 2 pi times the exponentials of the term minus a over 2 times x minus x0 to the square, which is approximately by the normal distribution with parameters x0 and 1 over a in the multivariate setting where x is in alpha, the real number r to the d, where we have log of f of x is equals to log of f of x0 minus 1/2 times x minus x0 to the transpose times a times x minus x0 and so on, where a is the Bayesian matrix of second derivatives, that is a equals to minus double delta of log of f of x, where is when x equals to x0. The derivative is taken from that. And the Laplace approximation is then f of x equals to the absolute values of a then to the square root divided by 2 pi to the d over 2, then times exponential of the term minus 1/2 times x minus x0 to the t times a times x minus x0, which is approximately by n d of the parameter x0, a to the inverse. And having now discussed how to approximate, we can now use it for the posterior density. Wmap, which is the mode of P of W conditioning on Rx, is taken as the mean, and the covariance matrix is given by the inverse of the matrix of the second derivatives of the negative log likelihood. That is, Sn equals to minus double delta of times log of P of W conditioning on alpha x, which is equals to S0 to the inverse plus sigma t summing for all the term y to the t times 1 minus y to the t times x to the t times x to the t times transpose. We then, x to the t times x to the t its transpose. And we then integrate over this Gaussian to estimate the class probability P of C1 conditional x, which is equals to gamma, which is equals to the integrations of sigmoid of W transpose times x times Q of W dW, where Q of W is approximately by the normal distribution, the Gaussian distribution with parameters Wmap and Sn to the inverse. The further complication is that we cannot integrate analytically over a Gaussian convolved with a sigmoid. If we use the probit function instead, which has the same S shape as the sigmoid, an analytical solution is possible. This is proposed by Bishop in 2006.